Weight and balance is the science of loading airplanes within their weight limit and CG range. Computing weight and balance begins with some weight and balance terminology. Weight is the weight of a loaded item in pounds. Arm is the distance of the loaded item from a reference point called a datum. The moment is a unit of leverage measured in inch-pounds and used to compute balance. CG is the center of gravity and is the point about which an object will balance, or its balance point. A datum is a common reference point from which all arms are measured. The scale balances when the moments on the left and right are equal. This can occur with various combination of weights and arms. All moments on the left are negative. All moments on the right are positive. Total moment equals the right moment minus the left moment. Subtracting the left moment from the right moment gives us a positive or negative or zero moment. A total moment of zero means the scale is in a state of balance. Notice the right moment of 5,000 inch-pounds minus the left moment of 5,000 inch-pounds equals zero. A total moment of zero means the scale is balanced. Moving weight to the right increases moment. Notice we moved the weight on the right side of the scale even farther right and the moment increased. We had a right moment of 5,000 inch-pounds and a left moment of 5,000 inch-pounds, giving us a total moment of 0 inch-pounds. Moving the weight on the right even farther to the right increased the right moment from 5,000 inch-pounds to 10,000 inch-pounds. Subtracting the left moment of 5,000 inch-pounds gives us a total moment of plus 5,000 inch-pounds, which imbalances the scale to the right. Now we will move weight from the left side of the scale to the right. Notice the total moment increases even farther to the right. Even though we were moving weight that was on the left side of the scale, we still imbalance the scale to the right by reducing the left moment from 5,000 inch-pounds to 2,500 inch-pounds. If we subtract the 2,500 inch-pounds on the left from the 10,000 inch-pound moment on the right, we get a total moment of 7,500 inch-pounds, which is 2,500 inch-pounds more than we started with. So as you can see, moving weight to the right will always increase the moment, even if we move the weight from the left side. Weight times arm equals moment is the formula used to find the moment. On the right, we have a weight of 100 pounds multiplied by a 50-inch arm, which gives us a 5,000 inch-pound moment. On the left, we have a weight of 100 pounds multiplied by a 50-inch arm, which gives us a 5,000 inch-pound moment. Subtracting the left moment from the right gives us a total moment of 0, which means our scale is balanced. In this example, we moved 100 pounds from 50 inches right of center to 100 inches right of center. This gives us a right moment of 10,000 inch-pounds. The left weight of 100 pounds remains at 50 inches and its 5,000 inch-pound moment remained the same. Subtracting the left from the right gives us a plus 5,000 inch-pound total moment, which imbalances the scale to the right. In this example, we just moved 100 pounds on the left side of the scale from 50 inches to 75 inches, giving us a left moment of 7,500 inch-pounds. Subtracting the 7,500 inch-pound moment on the left from the 10,000 inch-pound moment on the right gives us a total moment of 2,500 inch-pounds. The scale is still imbalanced to the right, but the 2,500 inch-pound imbalance is less than the 5,000 inch-pound imbalance we previously had. Shifting weight to the left reduces the moment. It makes no difference if we move weight from the right side to the left or if we move weight from the left side farther left. The result is the same. We currently have a scale that's 2,500 inch-pounds out of balance to the right, and we want to restore balance to the scale. We want to move 100 pounds on the right side far left enough to reduce the moment from 2,500 to 0. Total moment divided by the weight equals the distance that we need to shift. So if we divide 100 pound weight that we want to move by the total moment of 2,500 inch-pounds, we'll get the distance that we need to move left in order to reduce the moment to 0 and restore balance to the scale. 2,500 inch-pounds divided by 100 pounds equals 25 inches to the left, which gives us a right arm of 75 inches. We can validate this answer by looking at the result. If we started with a left weight of 100 pounds and a left arm of 75 inches, we have a left moment of 7,500 inch-pounds. After moving the weight on the right, we are left with a right weight of 100 pounds and a right arm of 75 inches, giving us a right moment of 7,500 inch-pounds. Subtracting the left moment of 7,500 inch-pounds from the right moment of 7,500 inch-pounds gives us a total moment of 0, which restores balance to the scale. We learned how to balance a scale on one balance point. Balancing an airplane requires a different technique because they are approved for a range of weight and balance combinations. First thing we need to do is move the datum from the center to a location in front of the plane. Most airplane manufacturers do this. We will measure all weights and moments behind that line, and all moments become positive. Notice the arm length for each of the loaded items. Airplane manufacturers give you this information in their weight and balance section so you can solve weight and balance problems for the airplanes they build. This example gives us some weight and balance information for our plane as supplied by the manufacturer. The information on the left is the limitations we must comply with. We insert weight and balance information in the table on the right and use that to solve weight and balance problems. Notice the weight column. You will find a series of numbers. The labels in the left column tell you what the weight is. The basic empty weight does not have an arm because it has a weight and a moment. The arm is a number we use to find a moment when we don't have one. Notice the basic empty weight moment is 99,600 inch-pounds. but there are no other moments listed. We need to solve for these. We find the moments by multiplying the weight times the arm and writing the moment in the column to the right. For example, multiplying the weight of the pilot and the front passenger, 350 pounds, by the arm of 80.5 inches gives us 28,175 inch-pound moment. Insert that number below the 99,600 pound moment and repeat the process for the remainder of the weights and arms. Now that we have all the weights and moments calculated, we must add the weight in one column and add the moment in the other. In this case, we will not subtract moments. All moments are positive, so we will only add moments. Total weight should have been 2240 pounds, and the total moment should have been 206,190 inch-pounds. Weight times arm equals moment divided by gross weight equals CG is the formula we use to find the CG. 206,190 pounds divided by 2,240 pounds will give us a CG of 92.04 inches. That's 1 inch forward of the aft limit.